Hi everybody, it's Miss Peachy from your WCA physics class, and today I'm going to be doing a supplemental lesson on momentum and impulse from chapter 6 of your physics textbook. We're going to explain what it is and also go through some practice problems so that you better understand kind of how those concepts are related to one another. So momentum is just really a quantity of motion. That's what Newton described it as. Isaac Newton described it as quantity of motion. And it is mathematically defined as mass times velocity. So as you notice, it has some similar mathematical characteristics to energy, kinetic energy. Kinetic energy being 1/2 mass times velocity, or the square of the velocity, right? So they have the same variables in them, they're just slightly differently multiplied and stuff like that with each other. So that's what momentum is. So an object only has momentum when it is moving. When an object is not in motion, it doesn't have momentum. Similarly, when an object is not in motion, it does not have kinetic energy, okay? So that's something to think about as well. And an object's momentum is going to increase depending on whether or not it's heavier or more massive, or if it's traveling at a faster velocity, just like kinetic energy would as well. So they're directly related to one another, as you can see. The other part of what we're looking at today is impulse. And impulse has to do with the time that a force is applied. So most of the time when we're looking at momentum, we are looking at collisions. So an object is going to collide with another object. And that collision can be a very quick collision or it can be a very slow collision. And so the time that force is applied in that collision is the impulse. So the impulse has to do with the time of the interval multiplied times the force, which would give us a change in momentum. Okay, so how quickly or slowly that force is applied, and how does that affect the change in momentum of an object. So I'm going to explain that in a little more detail here using some math, some formulas, and some different scenarios, but I gotta use my handy dandy notebook for that. So you guys are probably too young for Blue's Clues at this point, but that's definitely a Blue's Clues reference. All right, guys, so I'm going to switch it from me to my notebook, which is so much more comfortable for me anyway. First, let me change the camera so that we're not getting a full face shot, and then we'll get it larger, and then I'll do some fancy zoom in and stuff like that, because you know this is all high tech, right? I mean, this is just as high tech as you get here. Whew, flipped it around. Zoom in on my notebook. And I got some reminder to call the pharmacy later on today to get a prescription refilled. So yeah, that's cool stuff right there as well. So remember, momentum itself is pretty easy to calculate. I'm not going to spend a lot of time going through practice problems with momentum because it's what I would always refer to as plug and play physics. You are just plugging the numbers into a formula and solving, right? Pretty simple stuff. So momentum is lowercase p. That's momentum. I'm going to lock the focus, and that's equal to mass times velocity. So then the units for momentum becomes kilograms meter per second. Okay? It's not, remember, a Newton is a kilogram meter per second squared. That would be force. And energy is joule, which is a Newton meter. So they're all related to one another, though. So it helps when we're doing some of the other math problems to be able to realize which units can cancel and that kind of stuff. So problem that's given, sample problem A says a 2,000 250 kilogram pickup truck. So we got a pickup truck here. Let's see. Gonna do a little art for you. Okay. 2,250 kilograms. Has a velocity of 25 meters per second. It says to the east, but since I drew my pickup truck backwards, we're going to change that to the west. So its velocity is 25 meters per second to the west. Because remember, velocity is a vector. What's the momentum of the truck? Well, momentum is mass times velocity. So 2,250 kilograms times 25 meters per second, which gives us 56,000 kilogram meters per second to the west. Okay, so I mean, really simple plug and play, that kind of stuff, right? And again, momentum is a vector, so it's giving us both the quantity and the direction. So again, I'm not going to spend a ton of time going through this simple 3-variable problem. Not too difficult to understand. So the next thing your book talks about is the impulse momentum theorem. And I think this is where it becomes a little bit more tricky. So when you're talking about impulse, remember this is the length of time a force is applied in order to change an object's momentum. Just write that down, because that's in my own words there. Length of time a force is applied in order to change an object's momentum. Okay? So let's think of an example here. So this is a classic example, right? So if I'm dropping a raw egg onto the floor, and let's say that floor is made up of just ceramic tile or whatever, right? Versus if I drop the egg onto a pillow, how does that change the situation? Because in this situation, we could say that the egg is dropping with a velocity of, say, 3 meters per second in both cases. And let's say the egg weighs half, oh my gosh, that's a pretty heavy egg. We'll call it 0.05 kilograms. So as you can see, the numbers tell us, according to momentum, P equals m times v, that both of these guys have the same momentum. However, from experience, we know that the egg that hits the concrete or the ceramic tile floor is going to splat, and you're going to end up with a totally broken egg here, right? And the egg that hits the pillow might just bounce and roll off, or just kind of like settle right into the pillow. It's not going to break. No, it's not going to break, guys, I promise you. So the difference here is not an object's mass or velocity. The difference is in how much time it took to slow that egg down. So both of them had to stop their velocity. This egg had to stop its velocity quickly. This egg had more time to stop its velocity. So the force applied to this egg is much less. Same principle behind why we have airbags in cars and seatbelts as well, because it slows down the amount of time it takes to stop your body's motion, and therefore imparting less force to your body. So the impulse momentum theorem says that the force multiplied by the change in time, delta t, is equal to the change in momentum. Remember that momentum is mass times velocity, and the mass isn't going to change. It's not like the egg is going to suddenly lose or gain mass, but its velocity is going to change. So we can rewrite this as force times delta t is equal to mass times the final velocity minus mass times the initial velocity. And that's the truth, right? So what's changing, though, remember, is the time it takes to do that. So let's look at an example of the force or impulse momentum theorem. And let's see, I'm actually going to go ahead and put that onto the next video. So we talked about what the impulse momentum theorem is, and then we'll go through an example or a couple of examples in the next video because we're running out of time, okay? So I'll just put up here, see impulse momentum video number 2. I only get 15 minutes per video. So, all right, so go ahead and check out the next video recording, and that's going to give you some examples of the impulse momentum theorem.